Started? Can you guys hear me in the back? Hear me okay? Okay. Well, welcome to session 249. I want to thank you for coming and spending time with me today where we'll talk about sensor hardware in Windows 8. My name is Gavin Gear, and I'm a program manager at Microsoft. And I've been at Microsoft for 11 years. And unlike a lot of my colleagues at work, I didn't study computer science or computer engineering. I'm actually a mechanical engineering guy. But over the course of my studies in mechanical engineering, there were a couple things that really resonated with me. One was writing software. I got hooked on writing software for the Windows platform. The other was data acquisition and control systems. To me, there was just something truly fascinating about being able to write software that reached sort of beyond the confines of the box to reach out to the surrounding environment and capture data. So fast forward to 2007, I led the team that worked to design sort of the native support for sensors in Windows. And this was just a really exciting time, and just I couldn't have asked for a better job and a better assignment. But that was just laying the foundation. In Windows 8, we've really built on that foundation to make sensors first-class citizens in this sort of hardware ontology for Windows, especially on mobile form factors. So that's what we're here to talk about today. We're going to start by talking about the different opportunities that there are nowadays for sensor hardware and for sensor apps. We're also going to talk about some of the challenges that we've encountered in Windows 7 and in Windows 8. We'll talk about the investments that we've made in sensor features to really provide that top level of support for sensors in Windows 8. We'll then move on to talk about an exciting new area of sensor hardware and software technology, which is sensor fusion. We'll talk about what sensor fusion is, we'll talk about what sensor fusion does, and we'll talk about how you can implement support for sensor fusion in your hardware and in your drivers. We'll also talk through some specific engineering considerations if you're going to build PC hardware that incorporates sensors, or if you build sensors and you need to support partners that are integrating that sensor hardware on different PC platforms. Then we'll talk about the major investments that we've made at Microsoft in certification for sensors. Because these sensor systems are complex and the data is really critical to applications, we really want to make sure that system-level features and applications behave reliably and consistently on all of our different hardware platforms and different PC form factors that implement support for sensors. So when you leave today, you'll have examples of how to design PC hardware that uses the latest cutting-edge sensor technology. And you'll also learn how to build a Windows 8 compliant system that will work consistently and reliably and really represent the best of breed of sensor-enabled mobile PC hardware. So sensor technology and apps are really evolving at a rapid pace. Just 10 years ago, there was a whole class of sensor technology that was really dedicated to niche applications like robotics and avionics. And today, we've seen components of that cutting-edge sensor technology propagate to consumer electronics devices. Applications have taken a larger and larger dependency on sensors. Initially, it was sort of novelty applications and basic interactions. Today's applications are taking more and more advantage of sensor technology to adapt to the environment, to do exciting types of interactions. And we'll see examples of some of that today on Windows 8. So let's walk through some of the opportunities. Yesterday's rocket science really is today's consumer electronics technology. 10 years ago, some of that sensor technology that was for things like avionics, like a autopilot system for a commercial jetliner, has actually trickled down into the everyday devices that we're all familiar with. So as an example, I have a remote control helicopter that has gyro-stabilized flight control. And it just is amazing. It's totally rock solid, and it makes the helicopter something that I can actually fly. That helicopter costs $50. So this technology, the way that it's moving, the way that it's changing, is truly exciting, and it's opening up new possibilities for consumer electronics and for Windows hardware. Sensor fusion really takes these capabilities to the next level. Individual sensors are useful and are really required for today's consumer electronics and mobile PC hardware. But when we take multiple sensors and we combine them together, we get something that's truly more capable and more powerful than what we could do with the individual sensors. Sensors allow devices and apps that run on those devices to adapt to different environments. And this means that consumers can use those devices and use those applications in more places and in more different environmental conditions. So we're really increasing the usefulness of the devices, and we're creating a more ubiquitous experience for the apps that runs on those devices. Sensor part costs are decreasing at a rapid rate, while their capabilities are actually increasing at a rapid rate. To give you an example, in 1998, if you were going to build a device that used a 2D accelerometer, in volume you could pay somewhere between $5 to $9 for that 2D accelerometer. Today, if you build a PC with a 3D accelerometer, you're going to pay under $1 for that 3D accelerometer that has 50% more measurement axes, has better data, and is much lower in cost. So the capabilities are impressive, and the costs today are more incremental. So where there are great opportunities, there are great challenges, right? During Windows 7, we helped some of our hardware partners incorporate sensor technology. And I'll be totally honest, this was a bumpy path much of the time. One of the first problems that we encountered was we're asking our partners to put an accelerometer on a PC, for instance, but we don't really have a good way for them even to fundamentally connect the sensor to the system. Lots of typical low-cost sensors use simple peripheral bus technology like I2C. But a lot of the PC platforms didn't really support I2C in a way where the sensors could even get hooked up. So our partners had to improvise. And a part of that improvisation was writing custom drivers as well. And so there were challenges with the integration, and there were increased time delays due to the development and certification process. And at the end of the day, this wasn't the type of experience that we wanted for our hardware partners. The second issue that we encountered was just the performance and the quality of the data. There was a platform that we helped a partner with which used an accelerometer and a magnetometer to implement a compass. And while that type of hardware can support a compass scenario, it just didn't perform the way a user would expect a compass to perform, for example. We'll talk today about how we're addressing that with our guidelines and requirements for sensor hardware. We also want to create high-fidelity sensor experiences, but we don't want to degrade system performance in order to attain that high-fidelity sensor performance. So we'll see examples today of how we're providing hardware implementers the option to fully optimize things like sensor fusion. And finally, we had our partners dealing with hardware platform inconsistencies. So I talked about connectivity challenges and drivers. Well, often those connection strategies and those drivers were not portable from one hardware platform to the next. So essentially every PC that our sensor partners helped with and got contracts for involved a bunch of custom work. So this involves really a lot of collaboration, and we actually learned quite a bit from this whole process in Windows 7. So Windows 8 provides comprehensive support for cutting-edge sensors. Let's take a look at what this looks like. I have a demo for you, which is actually an application that a team of interns put together at Microsoft this summer that uses sensors. And you guys are the second audience that is going to see the sensor head cam in action. If our AV switch will switch over. There we go. Okay, so I have a Samsung Windows Developer Preview device, and I'm going to let you guys see what I see. So, this is actually an application that you guys can run on your device because it's pre-installed. So this is a Labyrinth-style application, just a casual game that uses the accelerometer to translate real gravity measurements into artificial gravity simulation for our game. So this game is a JavaScript-based Metro-style application, and it's able to access the accelerometer directly through a seamless API. As you can see, I'm really not that good at this, especially while I'm trying to demo. But it provides you an example of the type of experiences that users would expect on such a mobile device. Now, I want to point out a couple things here. First, this is the kind of sensor technology that's built into the devices that you guys have received here at the conference. The second thing is what we saw there wasn't just a game. It was a complete sensor system that's leveraging our in-box driver that we've provided in Windows 8 that supports all of the sensors that we feel are really important for mobile form factors. What mobile form factors are these? We've decided to take a strategic focus on tablets and convertible tablets. So any PC that has a slate mode or is a dedicated slate has the following sensors as standard equipment, because we feel these sensors are all critical to the system-level experiences that users expect and to the apps that will truly delight them and really extend the things that they're able to do on these types of devices. So every tablet or convertible tablet designed and certified for Windows 8 has the following: an ambient light sensor, which is used by the system to automatically control our screen backlight level. A full suite of motion and orientation sensors, including a 3D accelerometer, a 3D gyro, a 3D magnetometer, and the sensor fusion technology that binds these sensors all together to expose powerful new hardware capabilities. So these are the sensors. In addition to this, we've also got the Windows Location Provider inbox, which uses Wi-Fi access points and your IP address to pinpoint the user's location whenever they have network capabilities. So this is great news for application developers. This is a platform where if you're writing a Metro-style application for one of these types of devices, you know that all of this sensor hardware is going to be present and all this technology is accessible from your application using simple and seamless Windows runtime APIs. So you don't have to wonder or check if hardware is present. If you're targeting a tablet or convertible tablet, it's all going to be there. And so what I want to do now is move on to talk about the sensor platform features that we include in Windows 8 that makes this all possible. So I'll start with the core sensor platform components. The first thing that we did in Windows 7 is we thought about how sensors ought to be modeled. We grouped sensors into categories, and we defined sensor types that identified the type of sensor or transducer that's being exposed through the platform. We defined properties that expose metadata that describes the sensors. We defined events that sensors can use to trigger when new data is available or other sensor-specific interactions are detected. All of these types of metadata are included in the WDK in sensors.h. And this is a file that includes all of the unique IDs that essentially create these profile definitions for each of the sensors that your hardware implements support for. We've also got the Sensor Device Driver Interface, or DDI, which really boils out all of the redundant code that you would need to include in your driver, all of the common interactions that are shared among sensor drivers, and it provides that in a utility library. So there's a simple outgoing interface that you use from your UMDF driver, which is a user mode driver. We'll talk about that a little bit more when we talk about the architecture. To trigger new events, to initialize things. You also implement a callback in your UMDF driver to respond to incoming requests. So when apps want data or when they want to examine properties, your callback gets called, you supply the data, and hand it back to the applications. We've really streamlined the process for writing and debugging these drivers. The Sensor API provides the standard application level interface. And in Windows 7, this was Win32 API that was sort of a universal API for all of the sensors using the definitions. In Windows 8, we've extended this to more domain-specific APIs for each of the sensors that we talked about for the tablet and convertible tablet form factors. And those are the key scenarios that we really want to have Metro apps take advantage of. So we have these Windows Runtime APIs that really make it easy to implement simple interactions and also to tap into the power of things like sensor fusion. The Location API is much like the Sensor API, but it provides a layer of abstraction between all of the different types of location providers on the system and the application. So based on the age of the data and the accuracy of the data, the Location API provides that prioritization and transition logic so that apps can just access location in a uniform and seamless way. Win32, again, for Windows 7, but in Windows 8, we've added support for the W3C API, which is a standards-based API, and the Windows Runtime has its own very clean and simple interface for location access as well. Finally, we have the Sensor Service, which is an NT service. Think of it as a background system-level process that runs, and it actually starts on demand only when the appropriate sensor hardware is present. So on systems without sensors, like a server or a desktop, the sensor service isn't running, taking up memory and CPU. On the systems where sensors do matter, where the hardware is present, this sensor service starts when the system boots up, and it monitors sensor data to do things like control screen brightness and that kind of thing. So let's talk a little bit more about the built-in sensor features. So the first built-in feature that we actually delivered in Windows 7 was adaptive brightness. So when you include a built-in ambient light sensor and you have a dimmable display, a built-in display, which could be a laptop or a slate or even an all-in-one PC, adaptive brightness can automatically tune the brightness level based on different lighting conditions, that kind of thing. And this is something that when you're shipping a system needs to be thought through end to end in terms of smooth transitions in brightness levels, in terms of fine-tuning what we call the ambient light response curve, that kind of thing, so that for a lighting environment you get the right response for the display. The second feature is auto screen rotation. This is a really important investment that we've made for Windows 8. In Windows 7, there were certain challenges related to graphics and related to display modes and that kind of thing. And we really had difficulty getting a good experience out of rotation. And third parties had to actually implement that on their own. In Windows 8, we've really taken an across-the-board look at sensors and graphics, and we've provided an auto-rotation experience that's snappy and smooth and delightful. In addition to that, applications can suppress auto-rotation in order to provide their own tailored experience for the device rotating. So this is a great way to have system-level functionality and apps all kind of running in unison. The Windows Location Provider, again, is this software-based location provider virtual device that uses Wi-Fi access points and your IP address to serve up location data. So on systems with mobile broadband hardware, you've got GPS. You've always got the Windows Location Provider, regardless of what form factor you're running on. So for tablets and convertible tablets, your users are able to use apps that access their location, and they'll have that location data most likely, regardless of whether they're indoors or outdoors. So these are the features that we built in Inbox that do something with the system and with sensors. An important new capability as well is the work that we've done to support Inbox driver functionality for sensors. So what we did was we partnered with some of our partners in industry to work on new standards for sensors in what's called HID. HID was originally all about human interface devices. But over the course of the years, it's been permutated, and its functionality, and the standards that it covers has really been extended to include other things. And sensors is now a part of what the HID standard provides support for. And this is really critical because this really provides us with a standards-based hardware interface that we've been able to act on in Windows 8 by providing this HID sensor class driver. So if your device firmware is able to support this HID profile, you can take advantage of this HID sensor class driver. That's what we saw with the Labyrinth game, and that's what you'll see with all of the other demos on the Samsung Windows Developer Preview device. All of the motion and orientation sensors use a microcontroller. That microcontroller implements the HID profile for sensors. And because of that, there was no driver work for STMicro to do in order to support these sensors. So this is great because it allows our hardware partners to focus on their hardware and to not have to think as much about driver development, that kind of thing. And this HID sensor class driver covers all of the sensors that we talked about, the ones that are standard equipment on tablet and convertible tablet, but it does support other sensors as well. We've also got the ACPI ambient light sensor, which provides sort of a legacy approach to connecting ambient light sensors. And this is really most relevant on x86 and x64 platforms. And it allows more flexibility under the covers with regard to how the ambient light sensor is hooked up. And again, you have no driver work to do if you're using that driver. So, we've talked about the hardware, we've talked about the features and drivers. Let's talk about sensor fusion. Sensor fusion really is a case where the whole is greater than the sum of the parts. What is sensor fusion? The definition is actually quite simple. Sensor fusion is really taking multiple sensor inputs and using the combination of those sensor inputs to refine sensor outputs or to synthesize new sensor outputs. And I want to show you a demo of sensor fusion in action. Again, we're going to switch over to my sensor head cam here. And this is a demo that you saw if you were watching the keynote. It's a very simple application called the Metro steering wheel, and it uses the inclinometer that's built into this device. So we're using the yaw axis data off the 3D inclinometer. And what we're actually seeing here is sensor fusion in action from a very simple JavaScript-based Metro-style application. So I can turn the wheel and by just turning the device. And a couple things I want you to see specifically here are it's very responsive. I can turn the device rapidly and the wheel turns rapidly. That's very difficult to attain without sensor fusion. Another thing that we can do is actually put the device down on a flat and level plane and turn the wheel, and we can see that respond. So the sensor fusion engine is actually able to transition from using gravity to using the magnetometer, depending on how the device is oriented. And the yaw axis always represents the rotation of the device around the axis pointing out of the screen, which is the same axis that we have for a steering wheel in a real car. Another thing I want you to notice here is that it's jitter-free. If I'm holding the device stationary enough, the wheel doesn't move. This is because of the high data rate sampling and filtering that goes on low in the microcontroller, low in the stack. And we're able to get high fidelity data without getting a whole bunch of events, that kind of thing. So one more thing I want to show to you is specifically the ambient light sensor support. So what we can do is tap on the headlight switch here. I'm going to illuminate the light sensor here. And so we can go to an auto mode, and if it gets dark enough, did you see that? Let me try and get it dark. There we go. So we can actually have the dash lights turn on automatically from day mode to night mode. So that's just a really simple interaction, but that extra little bit of functionality that delights the user. And if we're feeling impatient, we can also honk at people. So I won't do any Southern California jokes there, I promise. So again, that's an example, a simple example of sensor fusion in action. And as Mike mentioned in the keynote, every time I update the position of the wheel, that's 3 lines of JavaScript. One to calculate the offset of the yaw axis, one to grab the transparent PNG image from our document, and another to apply a rotation transform via HTML5. So sensor fusion doesn't have to be rocket science. Sensor fusion can directly translate to things like casual games, that kind of thing. So I want to walk you through the hardware platform for sensor fusion for tablets and convertible tablets designed and built, certified for Windows 8. We start with the individual sensor components. These are down on the motherboard on every device. The 3D accelerometer measures linear acceleration and acceleration due to gravity. The gyro measures the rotational speeds around the X, Y, and Z axes. And the magnetometer measures magnetic field strengths around those same X, Y, and Z axes. Some of the data is merely passed through for the system and for apps to use directly. And there's really a lot you can do with just the accelerometer. We saw the Labyrinth game. You can do simple motion gesture detection. You can implement twisting gesture support with the gyro, that kind of thing. So raw data is definitely interesting. But what's really amazing is when we can take these 3 hardware inputs and fuse them together with sensor fusion. And deep down in the hardware, this enables high data rate sampling and different types of transition logic and filtering algorithms, auto-calibration. A whole lot of value and power is provided by sensor fusion. So what do we get out from sensor fusion? We get a 3D compass, which allows apps to know which direction the device is pointed, regardless of how the device is being held. We get our yaw, pitch, and roll rotations of the device in 3 space with the 3D inclinometer. We also get a device orientation sensor that exposes powerful data for things like direct 3D applications to use to model virtual reality experiences or augmented reality or first-person shooter games. A lot of different things we can do here. Now, under the covers, with sensor fusion, you really do need all 3 of these sensors. The accelerometer essentially gives the sensor fusion engine knowledge of which direction down is. So with a low-pass filter, you can determine the force due to gravity. The accelerometer and the magnetometer give the sensor fusion engine knowledge of which direction north is in a tilt-compensated manner, regardless of how the actual device is being held. But we can't really expose a seamless experience with just these two sensors because the magnetometer is a low data rate sensor and we have noise from these sensors. So we can add the gyro in, and that gives us a really fluid, responsive algorithm so that if we have electromagnetic interference, we can fill in the gaps. We can basically, for a short period of time, take the magnetometer out of the equation and do essentially dead reckoning for the heading part of that. When the device is being held up and down and is transitioning quickly, the gyro gives us that seamless responsiveness. And the great thing is, in Windows 8, apps don't have to think about all this. We've empowered our IHV partners to really innovate with things like auto-calibration, with power management, with the trade-offs between cost and performance and power. So I want to talk, actually before I go on to the next section here, I have one more demo. This is the best demo. I really like this one. This gives you an example of the device orientation sensor that I was talking about. And specifically, this is a Windows SDK sample from the DirectX team. And a colleague of mine, Jason Strayer, who's actually also giving a talk on Friday related to sensors, audio, and other forms of input for games, he modified this SDK sample so that it can use quaternion data to model a first-person shooter-style game experience. Actually, I have a little bit of a rotation bug there, but we can still use the application. So this enables us to look around in a virtual environment. And we can hit this fire button here to fire at targets. So regardless of how we're holding the device, we can interact with this as if we have a window into a virtual world. So we had to fine-tune the firmware for this demo, and we actually also had to fix a bug in our driver. But this gives you a really quick example of the types of experiences that app developers are going to be able to implement support for on Windows 8. And I will mention also that that's a Metro-style application. That's a Metro-style application that's written in C++ and taps into the full power of DirectX Math and Direct3D. And that's really unique value on the Windows platform. Our samples and APIs for games really make it easy for developers to innovate at a rapid pace. And by providing this type of sensor technology, we're really enabling app developers and consumers to have the next generation of experiences on these types of devices. So, how do you support sensor fusion in hardware? We're really advocating two different approaches to integrating the sensor fusion technology at the system level. The first is the hardware-based solution. That's actually the approach that was taken with the Samsung Windows Developer Preview device. There is a dedicated sensor processor on board. The dedicated sensor processor supports the HID sensor profile. It also has slave sensors that it interacts with to get data and to implement the fusion algorithms. And the advantage of this type of solution is really that first, it enables partners to develop turnkey solutions. So that with some engineering around placement and different things, you can pretty much bolt down a sensor processor, all of the sensors as more or less a package, and there's no driver work to do. So the other advantage is you're able to offload all of the sensor fusion algorithms onto the low power micro. So the downside is that you have to put the micro in place, and that can have an incremental addition to your cost. So the second option that we've been advocating is a software-based solution, where a sensor driver can do some or all of the sensor fusion on the main processor. And this solution enables lower BOM costs for PCs, but does require that specific sensor drivers are written and certified, that kind of a thing. So depending on the processor architecture, the power considerations, that kind of a thing, the software-based solution can also be an attractive solution. But if you are going to implement a software-based solution for sensor fusion, it's advisable to offload as much of the heavy lifting down onto the hardware if possible. So if you have a sensor component that has a DSP that can do some of the pre-processing on the data, your sensor driver can then just do the final fit and finish, integrate with the sensor platform, and pass the data more or less through with minimal power and performance degradation. So at the end of the talk, I actually have a link to a white paper that I've been working on. And that white paper goes into much more detail with regard to supporting motion and orientation sensors on Windows 8. Connectivity, firmware and driver implementation guidelines, form factor specifics. It's got a lot of really helpful information that you'll need if you're building such a solution. So let's talk through the sensor architecture and then cover some engineering considerations. In Windows 8, the real stars of the show are the apps. You guys saw during the keynote and some of the other general sessions some really exciting new experiences that users are able to tap into on Windows 8. With Metro, everything's fast and fluid. It's really easy to write the apps. There's really great opportunities here. We have these Windows Runtime APIs for sensors that just make it very easy for those apps to implement those features. We also support writing desktop apps, and that would use our Win32 API. And this is where you have more general interfaces, you get sensors by a type, you hook up event syncs. It's a little bit more code, but at the same time, it offers you more flexibility. So that's a good option for more vertical specialty scenarios. We also have the sensor service that's monitoring sensor data in order to implement system-level functionality. Below that sits the sensor API, which is the sort of fundamental core interface for applications to talk to. Below that, we have the driver. And in the driver's UMDF host process, we have the sensor class extension, which is the driver utility library that I talked about. This integrates directly with the sensor API. Your driver integrates with the sensor class extension. It instantiates it, it runs in proc, and that's really the proxy between your sensor hardware and the system and apps. I have two drivers here that I'm showing as examples. On the left, we have a third-party sensor driver. And this could be a sensor fusion driver or a light sensor driver. One of those situations where we need to write our own driver for whatever reason. On the right-hand side, we have the in-box HID sensor class driver. Both of these drivers integrate with the sensor class extension, and both of these drivers are loaded based on the enumeration of particular hardware. So this gives you a quick view of the overall stack and all of the moving parts and components that are at play when sensors are running on Windows 8. But I want to focus on one specific new capability that really solves a lot of the challenges that I talked about earlier in the presentation. And that's the fact that Windows 8 has great support and connectivity options for what we call simple peripheral bus sensors. These are the types of buses that most sensors support, like I2C or SPI, for example. So let's walk through what the stack looks like from the hardware up this time if we want to integrate a simple peripheral bus sensor. So we have our sensor at the very bottom. This could be a 3D accelerometer or a light sensor or really any type of sensor. The silicon vendor provides what we call a controller driver for the particular type of bus that it implements support for in silicon. So we have an I2C sensor here. Silicon vendor supplies an I2C controller driver. This I2C controller driver integrates with new driver level APIs called the Simple Peripheral Bus APIs in order to expose the data from that bus to other drivers. So if we want to write a driver, that's where our driver sits, up in UMDF, and it also interacts with these simple peripheral bus APIs. So if we want to directly access an I2C sensor, we can actually do that on Windows 8. This wasn't possible in Windows 7, and that was what really caused a lot of the big challenges that we had wiring things up and supporting things end to end. So this is big news for our ODM and OEM and IHV partners. Our sensor driver is really talking to two driver-level APIs around the connectivity in the sensors here. We have the simple peripheral bus APIs that we get and interact with our I2C device through. And then on the top, we have the sensor class extension. And this integration is necessary so that our sensor data can flow up through the stack end to end. So the great news here is the middle green box there, the sensor driver third party, is really all that you need to do from a software perspective. The I2C controller driver will be there for you, and then you can then very seamlessly support your simple peripheral bus sensors. I also want to encourage you all to really think of sensors not as individual parts, but as systems. It's easy to think of a sensor based on its spec sheet and to expect that to translate to a particular behavior or user experience. But it's really not so simple. I'll use ambient light sensors as an example. A light sensor could have a dynamic range of 1 lux to 50,000 lux. And you might think that that translates to what the PC would measure in real life, but in reality, there's glass on the top surface. There's coatings on that glass. The industrial designers like to kind of hide the sensors away. Below that, you've got potentially other optics or a light pipe, that kind of thing. And what this does is there's an attenuation factor that you need to think about. So in some cases, you might have as little as, say, 50% light transmittance. Well, if we have 100,000 lux, which is a typical outdoor ambient lighting condition, and we have 50% light transmittance, that means that we only have 50,000 lux getting to the sensor. So the actual dynamic range of our sensor is more like 2 lux to 100,000 lux, which is actually good news because that's what we really want. We require at least 30,000 lux because we want to be able to detect outdoor lighting conditions. But if you can go up to 100,000 lux, then you can support a wider variety of different environmental conditions. So the point is, it's a system. The ODM, who's potentially putting that top surface on, needs to work with the IHV to understand the capabilities of the sensors. Light scattering and dispersion and light leakage and all sorts of different issues that can really bite you in the end if you don't think about them up front and work closely as a team from the inception of the vision of the PC all the way through to the manufacturing process. Sensor fusion is another example of where this is really critical. These components are often sensitive to where they're placed on the motherboard, for example. The gyro, typically you want to be closer to the geometric center of the device. The magnetometer is in many cases very sensitive to its placement to other components on the system, like magnets for a Hall effect sensor, or radios for Wi-Fi or for 4G or for NFC. It could be a wide variety of things. So with sensor fusion, it's really kind of like you've got a whole bunch of different puzzle pieces. And over the course of designing and getting to manufacturing the PC on the different spins of the hardware, those puzzle pieces really need to be shifted around and the whole system thought of from a holistic perspective. And again, there's some guidance in the motion and orientation hardware integration white paper that we've documented to help with this. But really, it's the IHVs that know their technology from a sensor standpoint. So the key is collaboration. We really want to see early partnerships and to work through the various stages, layout diagrams and different types of analysis and testing and validation. It's really important to know what the desired outcome is and to make specific concrete steps towards that. Another topic that's really important is power management. So one of the investments that we've made in Windows 8 is Connected Standby. Did you guys see the demo that Mike Angiulo showed, showing the instantaneous power measurement? Really amazing stuff. I mean, really, really low power levels in Connected Standby. And then when the system comes out of Connected Standby, we see power go up. When we go back into Connected Standby, we come back down, apps clean up, and then we go down to that low level of power consumption. So one of the important parts of that equation is that sensors are off and powered down when the system is in Connected Standby. And from a driver level perspective, we've made that pretty simple. It's pretty much as simple as monitoring a client count. And we do a lot of the heavy lifting for determining when your sensors can power down for you. More detail than we can really go into here, but a really important consideration. The other thing I want to talk about with power management is sort of this power state machine that's really critical for things like sensor fusion. When the system boots up, really the only thing that's going on is screen auto rotation by default. And when only screen rotation is occurring, we really want to see only the accelerometer powered up. You know, we also have the gyro and the magnetometer, but unless someone's using them, they're not needed, and some of those sensor components are power hungry. So active power management is critical. When an app starts up that uses any of those sensor fusion sensors, the hardware needs to respond by altering that power state machine. So if we have an app that's using, the device orientation sensor, the gyro needs to get powered up. The magnetometer needs to get powered up. And then the device orientation needs to be determined in a reasonable amount of time. You know, if a game is starting and they have a 2-second splash screen, ideally when that splash screen is done, the sensors are brought up and the net knowledge of device orientation is ready for apps to leverage, that kind of thing. So power management is critical. We've made major investments for Connected Standby and for when apps are suspended and resumed. These investments directly translate, even through our HID sensor class driver, to more simplified implementations of this advanced power management. So finally, we have made major investments in sensor certification. We had some really big challenges around sensor fusion and around optoelectronics. And what we've done with sensor certification is provided a set of tests that you can run on your hardware, and this really helps you to optimize the experiences and the reliability and the consistency of the data. Because with Windows, we have a diverse hardware ecosystem. That's one of our great strengths. What we need to do is back that up with really consistent system level and application level experiences. And Windows certification is a key part of attaining that goal. So, to recap, Windows 8 makes it really easy to use sensors in your Metro-style applications. We've got the Windows Runtime APIs for sensors that are simple and easy to use. They also provide applications the power to take it as far as they want with sensor fusion and with 3D experiences, that kind of thing. We give developers the tool and language options when they go to write apps that make developing the apps, running the apps, and debugging the apps simple and straightforward. Windows 8 also makes it easier to integrate sensor hardware. With our HID sensor class driver and our ACPI light sensor driver, with the support that we have for simple peripheral buses, and with the documentation and samples that we have in the Windows driver kit, this is going to empower you to rapidly develop systems for Windows 8 that expose these hardware level capabilities. I do want to quickly mention that in the WDK, we have a driver sample that really ties these concepts together. And that's the accelerometer sample using simple peripheral bus technology. So if you want to know how to use the SPB APIs, if you want to know how to translate raw values into sensor data primitives that are exposed up through the platform, this is a great starting point for you and really can empower you to more rapidly support your hardware. We've also got a bunch of great related sessions, some of which have already occurred and some of which you can still see live. These are all recorded, so you can catch all of these after the fact. Building great Windows 8 systems, 774, is a great high-level overview of device-level support in Windows 8. 781, which actually went on in the last hour, was sort of the software developer counterpoint to this talk. So here we focused on the sensor hardware. In that talk, you can learn more about what apps can do with sensors and these APIs that we've been talking about. On Friday, my colleague Jason Strayer will be presenting at session 754, which is this input talk for Direct 3D apps, for controllers, and for audio, and for sensors. So if you want to know more about what app developers will be able to do on Windows 8 systems, that would be a great talk to go see. And finally, the introduction to low power buses for Windows 8 talk will go into more detail regarding these low power bus APIs or simple peripheral bus APIs and how that architecture works and what you need to do to use it. So we've got a lot of great content. Online, we've also got both sort of conceptual API, device driver documentation that you can go and read. Here's a link to the white paper regarding integrating motion and orientation sensors that I was talking about. We've also got the dev centers that can provide a great level of documentation for you to go explore as well. If you need to contact my team directly, you can email this senseext alias, and we can provide you pointers to the right type of documentation or help you with specific issues that you're working through. So I really want to thank you all for coming. I'm really excited about Windows 8. I'm also really excited about the hardware that you all are going to build that's going to really make Windows 8 shine and that's going to unlock these great new capabilities that we've talked about today. I would appreciate it if you could go online and fill out the feedback form for this session, because that helps us to know what worked for you and what content you enjoyed and how we can bring you these types of high-quality events in the future. So with that, I want to save a few minutes for questions. If you guys do have questions, you can line up at the microphones. And if you don't want to speak publicly, I'll also be available after this session to answer specific questions that you may have. Anyone with questions? Oh, we've got someone.
Yeah. So you mentioned I2C bus support. What about SPI bus?
So SPI, I would refer you to one of my colleagues. Mm-hmm. SPI and I2C, I believe, are sort of two of the primary interfaces that we support. It does require that a controller driver be present. Mm-hmm. But for additional details, since that's not my area of expertise, I'd point you. Even the senseext alias would be a good place to start there.
Thanks.
Thanks.
So for Windows 8 tablets and convertibles, the three sensors you outlined, mm-hmm. those are mandatory requirements. Is that correct?
The question is, for Windows 8 tablets and convertible tablets, the three sensors are required. That's true. In order to pass Windows certification for tablet and convertible tablet, you've got to have a light sensor present, accelerometer, compass, gyro, and the sensor fusion. And then there's system-level tests, and there's device-level tests. For each system that gets shipped, all the tests need to run If you're running device level tests, some of them will leverage our driver. And it's really the behavior of the firmware and the device that's being tested at that point. But yes, they are required for Windows 8.
Okay. And this is all Windows 8 only. This
Correct.
framework is not on
Yep.
Windows 7.
Anything with a tablet mode for Windows 8, those are required sensors, but just for Windows 8.
Okay.
Yep.
Thanks.
Oh, we've got another daring person here. Nope. Sneaking out? Okay. All right. Thanks again, everybody. Oh, one more question. Sorry.
So you talk about also this sensor were related to the Connect Standby.
Yes.
But from the session of the Connect Standby, they talk about it. It's just put on for the APP side. Java won't impact it. So can you make it a bit clear for such place?
So the question was about connected standby specifically. We can't go into all of the nuances of how it works, but the components that we have in place, the sensor platform components and API level support, essentially notifies your device when there's clients that have basically accessed the sensor or have departed, essentially, and released a handle to a sensor. So your driver or your firmware has collective knowledge about how many clients are accessing the sensor, and the connected standby code that you need to write is really around when there are no clients, I can power down my sensor device. So I'm sorry if that's an overly simple answer, but we can help you offline if you need to know more details about connected standby. Okay, thanks again, everyone.